All right, so let's get into it. So today we're just super happy to announce StaexD, a new version of our product for distributed, decentralized container and also native application orchestration. So the Staex development stack as we have it today has existed so far with Staex MCC, which provides peer-to-peer networking and service discovery on large-scale distributed networks, especially for IoT and robotics in industry. And now we are super happy to present StaexD, which enables with Staex MCC the deployment of applications on top of this fully peer-to-peer network. So before we go into what our product, what StaexD actually does, and how it differentiates from the competition, let's go over the current standards that are out there today. So some of the popular orchestration tools for software currently are Kubernetes, which include micro-K8s, K3s. There are other different versions of Kubernetes that are out there, and this is probably one of the biggest standards for orchestrating containers on cloud infrastructure. The second one would be HashiCorp Nomad. It's similar to Kubernetes, but it is also an alternative where it actually also includes the support of orchestrating native applications to different devices that are running Nomad, but essentially provides the same experience as Kubernetes. We then have Rancher, which is for managing Kubernetes clusters, and Docker Swarm, which is a lightweight version, let's say, of Kubernetes. Now, all of these, what they have in common is the one common goal for DevOps to be able to deploy and manage deployments on systems. But they come with some drawbacks, especially when we were looking into IoT and robotics. So all of these products were designed for data center usage, which means that they work well in certain singular clouds. So let's say AWS, or if you have on-premise servers that you want to link up, you could start a Kubernetes cluster, for example, and you'd be able to manage it perfectly fine like that. However, it starts to break down then when you end up going to multi-cloud environments, or if you have large geographically distributed hardware. And then you start to see the issues that I list here below. So with IoT, you're dealing with a lot of intermittent connectivity that's on the edge. And these former platforms do not really handle that very well. They expect kind of perfect connectivity, or at least very close to perfect connectivity without very much latency. And we know that in the real world, that doesn't really exist, especially with IoT. So that's one of the drawbacks to these traditional systems. Additionally, they require complex configurations and know-how to set up actually properly. And like I mentioned before, multi-tenant infrastructures. So let's say you're trying to collaborate with another company, or if you're using different cloud services, those are difficult to implement using these traditional systems. And that's because they rely on centralized services that basically control the centralized controller works with workers that are in local environments. But when you start spreading the workers out or have multiple controllers over these different environments, you actually end up with a lot of issues about who's actually controlling what. Can I connect to these devices if they're in some other type of cloud infrastructure, for example? And that's why the multi-tenant infrastructures are difficult to implement. And on a more practical level, they have large storage and memory requirements. So even the software itself requires 40 megabytes alone for K3s, which was supposed to be designed for edge. Nomad also is 50 megabytes. And these don't work for IoT devices. They're just simply too large. And they also store a lot of data when they run. So these smaller devices that are already resource constrained because they need to operate on low power, et cetera, they wouldn't be able to necessarily run these pieces of software. And lastly, more on a principle note, centralized control planes and service meshes, so how you look up what software is actually running, are not highly fault tolerant when you're using, when you start to expand to larger systems. So if you're losing connectivity to the control plane from your edge device, how do you actually control it? What happens is if a hacker actually takes over one of those and then they have access to a bunch of different devices that are below them. So it ends up being a very nice target for failures or hacking. And that's what all these previous systems have relied on, is this kind of star-shaped central control, and then going out to the edge nodes. But we know that in the real world, that's not how it actually looks for IoT. So exactly, they aren't designed with true edge IoT in mind, where edge devices can communicate with each other. They need to be able to interact without the controller being available sometimes over mobile networks, et cetera. And they also need to be suitable for small form factors. And so that's why we created StaexD. So StaexD is optimized for resource constrained devices. It is energy efficient, which goes, I guess, some parts hand in hand with our optimizations for the small size. It's also fully distributed and not centralized at all, which means that any of the StaexD nodes can function alone with a group of other edge nodes and still function perfectly fine, so without any type of centralized controller. And it also, we wanted to make sure that it was easy to migrate to from these previous systems, from Kubernetes, for example, and also integrate with other systems very easily. And so I'll break these down here, exactly what each of them mean and what we've actually done. So StaexD has a small binary size. It's only 5 megabytes or even 4 megabytes for ARM devices. Which is a significant drop in size compared to the previous software that I mentioned. It's also written in Rust, which is a cutting edge programming language that offers really high performance and ensures that we have a small memory footprint on these devices. So we actually enable these IoT devices to actually have more application or more space for computation for the actual applications that have to be running out there on the edge. Additionally, we wanted to reduce the energy since a lot of these devices are going to be running on batteries, robots, IoT devices that are sitting in the field. And one of the largest things that causes the battery drain is actually networking. So we stripped down the networking transmission so that we are pushing out the least amount of messages possible while still providing enough data to actually function. And we also reduced the amount of CPU time that was needed to process things on the device. So we actually were able to reduce it so that there's more idle time for the device and more of that battery can be used for the applications that are sitting on top. The distribution that we wanted to have as well, so we didn't have any centralized services, we got rid of all the dedicated management servers. So that means that there's no master worker model at all. It allows for edge-to-edge control. So it's actually truly between, let's say, two robots communicating with each other, telling each other, hey, I need this program to get started by you, or vice versa, or even integrating with other IoT devices. That can all happen on the edge without some type of centralized server that tells those devices what to do. It means that it's highly fault tolerant. Basically, the whole network would have to go down for it not to function, instead of just one singular piece, that singular controller like in Kubernetes. And it means it's also very, very scalable to thousands of nodes, and we don't have any performance loss. Whereas with other systems like Kubernetes, you wouldn't be able to scale to that level because of the need for more centralized services and communication. Lastly, our easy migration integration. We have implemented a simple application configuration, which is similar to other types of, so any DevOps engineer that's already working with Kubernetes, for example, would be able to understand. So it's based on YAML files. We can manage the cluster via a REST interface from any of the nodes that are in the network. And if we already have Kubernetes YAML files that are from previous projects, we can convert them over into StaexD application YAMLs, which means that migration to StaexD from other systems is very easy and intuitive. So what makes StaexD unique, and why are we able to have all of these benefits without, it seems kind of crazy that we're able to have such a small piece of software that still provides what those larger, more monolithic, let's say, pieces of software offer. It's because we've eliminated the idea of global state. So that means we don't actually need to have a blockchain for consensus, for example. We don't need to pass around information between all the nodes to say, hey, this is running here, that's running there, this service is located here. We can determine this information simply by making requests into the network, which means it's highly flexible. Nodes can come in and leave. and you don't have to worry about it going down. It also means that we don't have really high storage needs. So most of the storage that happens to determine what software needs to run, for example, only exists for a short period of time and then goes away. Which means that for smaller devices, we are actually very, we don't use a lot of resources and we're highly optimized for them. Because we also removed a lot of the networking overhead that exists in the other pieces of software, it means that we have a higher bandwidth for applications can use with the lower network chatter. And like I mentioned before, it also reduces the amount of energy used by the system. And so all in all, it means that we have created a product that has smaller hardware requirements and is more suitable for IoT and robotics and for the future of IoT and edge devices. So I can explain a little bit of how this actually works in more of an abstract way. So if someone makes an application request saying they want to start up or change how an application is running on the network, all we have to do is send a simple REST request, and which contains some information about what application needs to start and some other information about what the requirements are from the node. So how much CPU, so how much memory, etc. So we just make a guess. So we go to one of the nodes we think might have enough. And this is also, in a smaller network, it would maybe happen within one call. So I'm showing an example where it has to call a few different nodes to actually launch the application, but that's at a larger scale. So like I was saying, make the request to one node, find out, okay, it doesn't actually have enough memory. Then we go to the next. Maybe this one doesn't have enough CPU, or it's being used by too many applications already. Then we go to the next, same problem. And we eventually find one somewhere in the network that is able to then run this application. So this happens in very few steps. And even for thousands of nodes, it should take only several different calls, like maybe 4 different calls to different nodes to find a suitable place to launch the application. So it's really fast on a large scale network. It means that it's also very lightweight in overhead. And is actually perfect for IoT and robotics. And just like I said, it means that we can support networks of thousands and thousands of nodes without any type of performance decrease, which you would see in traditional systems like Kubernetes. So just to recap what we all support with StaexD, we can launch native applications, so applications that are not containerized, containerized applications like Docker images. We can actually deploy multiple different applications across different types of infrastructure. So between different clouds, so let's say Azure and AWS and something else. We can even do from the cloud to the edge, or we can even have a deployment pool that's between different edge devices that could all be running the same type of software, and it can happen in a fully peer-to-peer way. StaexD also allows you to stream telemetric data, so what like the CPU is doing. What the RAM is looking like, what memory. So you're able to actually find out what how your actual device is performing and what stresses it's under. We're also having role-based access control, which is still in development, but that will be in the nearer future. And this will all be available at the end of August 2022. So now, thank you for listening. First things first. I hope you found it interesting, and I would open it up now for questions.
Thank you, Andrew. I have one question from my side because you were also kind of describing the point about the centralization that you don't have kind of any central instance if you compare it to other systems. Can you maybe elaborate on it a little bit more, like how is then the architecture looks like and why this can be important for some of the IoT installations? Thank you.
Yeah, maybe I can go back to this image here, right? So we can see here that we've got a bunch of different nodes that are running out there. These could be different IoT devices. This could be located in the cloud, for example. I guess you can see all my pointer. but at the end of the day, there's no one singular entity that would have to be able to control all of these devices in a sense. In a traditional system, you'd have to have, let's say, the cloud here tell all of these different ones exactly what to run. And if this went down, then all of these edge devices don't actually know what they're doing. They have to somehow have some type of contingency plan of how to operate without being able to connect to this device or this cloud. But at the end of the day, if we remove this, we can actually remove the dependency on having this online all the time. So if it got hacked, or sometimes if one of the cloud services went down for whatever reason, which is not even a fault of your own, all these devices would still be able to function in the traditional way. You'd be able to send requests to these, and it would be able to spread out the information properly. So essentially what it's doing is removing this kind of central dependency and allowing for a lot more flexibility in deployments. If that answered your question, I hope.
Yes, thank you.
Any other questions?
Maybe also from the usage perspective, like how would I go about your system? How would I work with it? Like how much, you take on as an engine, on how much versus how much I need to kind of program into the kind of scripts myself.
Yes. Well, so it works essentially. Any engineer who's also worked with Kubernetes before, for example, would be able to pick up our system and use it very quickly. It simply just needs to be started, and so you start StaexD. It turns on, it boots up, it does all this stuff, sets its configurations, and then it would be as simple as making like an HTTP request with the application that you wanted to run or what you wanted to do with the network, and that's it. So it's really actually quite lightweight, and the learning curve is more in just how do I tell what my application needs. So how do I tell how much CPU, how much memory, etc. But that's simply a few days of learning.
Got it. Thank you.
Versus having to set up the full system, I guess would be that would be a lot more configuration and a lot more work. It could take weeks and months.
And also with regard to, because you mentioned that some of the Kubernetes scripts can be transferred, like is it like one-to-one mapping that is happening, or what is the rule of thumb there?
So we haven't been able to implement all the features from Kubernetes, for example, yet, just because it's such a massive, and it's been around for such a long time. There's a lot of community developments there. So it's not 100% one-to-one, let's say, but all the basic functions and being able to, we can convert that pretty much almost automatically. So like how to start up, how to scale up and down, how to shut down, etc. So we can do all of that.
Okay, got it. Thank you.
All right, then I guess if there are no other questions, thank you again for attending today. There's my contact, obviously, which you can reach out at any time. I can send you more information. And of course, if there are any questions after the webinar, then yeah, please reach out. So with that, I thank you again for attending today, and hope you have a great rest of your Wednesday.
Thank you.
Bye-bye.